Don't make them.
It made me so mad today. So unfair.
I don't know. What do you guys think? Perfect score first time? Would that be gong?
Yeah.
Okay. Yep. Yep. Perfect score first time would be gong. The extra credit, not good enough, but the gong, that's what motivates us.
I was literally halfway away from it. If I remember correctly, I like failed the. I think that might be the one they got. No, because the universe was the one they got. No, I was like, there was one test like. There was one quiz. Literally, I got like 3 right, and he pulled out the whole different colors of pen, and he was like writing all of them. I was like, they're so lucky. Oh yeah.
Okay. So first off, I would like to apologize to you. Let's go ahead and get started, guys. I don't know why I printed the formulas in this order. I did not mean to do this. That is ugly. The ones that go together are the ones that I've circled in the same color. So obviously the regular log formula goes with the natural log formula. And the exponential with any base formula goes with the e exponential formula. So you'll notice they are similar. There's only one difference in each of those. And if you'd prefer to memorize 2 formulas instead of 4, you can memorize the ones I circled in red. The reason why is if we actually followed this out for the E one, but using the A rule. So if we have this derivative, it'd be A to the U, okay, so instead it's E to the U, times natural log of the base here would be E, times chain rule du dx. Well, what's the natural log of E? 1. So then it puts you right back at the shortened version of the rule. You can do the exact same thing with the log ones. See how the log base A, that's any base, any number greater than 0, I guess. The simplified one with natural log, well, that's just base E. The natural log of E is 1, so that term just disappears. Otherwise, let's see. The base E ones are pretty easy to remember because notice the derivative of e to the u is itself times chain rule. So it's itself times derivative of the exponent. And then the derivative of natural log is 1 over the inside times chain rule. So 1 over the inside times derivative of the inside. It's these other two where you have to just remember, oh yeah, there's also got to be a factor of natural log in there somewhere. So let's look at our first one here. It's exponential, it's base e. Okay, so the derivative is the exact thing you started with, so just recopy it. 2x squared minus 5 times the derivative of the exponent. See how we got the u and then the du dx. So the derivative of the exponent would be 4x, just 4x. You can put the 4x in front, you can put the 4x behind, doesn't matter because it's multiplied. Okay, so for our next one, our base is not e, so we're going to use the a to the u formula. Again, the only difference is we have an extra factor in there, it's the natural log. So we'd say, keep the thing you started with, so 5 to the cosecant of x, whoops, times natural log of the base, so here the base is 5, and then finally chain rule, we got to make sure we derive whatever the exponent was. So what's the derivative of cosecant? Okay, let's see. Here we have a natural log. So looking up at the natural log rule, the derivative is 1 over the inside times derivative of the inside. Okay, so our inside is 12 over x, so we could say it's 1 over, and then the inside was 12 over x. You could also write it, yes, you could immediately simplify that if you like to x over 12, and then times the derivative of the inside. Okay, well, it might be helpful to at least scratch to yourself, okay, this is really 12 x to the negative 1. That way we can use the power rule instead of using the quotient rule. You can leave it like this. You can certainly clean it. Well, you might at least clean that up for me. How about... Hey, that's kind of nice. What do you know? Let's see, our last one has a number base that's not... Yes, a tip. Wait. Oh, I just didn't copy it. That's where it went. I was wondering. I was like, I didn't think it reduced this way. Yeah. Yep. There we go. That makes a little more sense, doesn't it? Let's see. Okay. So normally 1 over inside. Don't forget, since it's not e, since it's any other number, we got to multiply by the natural log of the base. So 1 over inside times natural log. The base was 3. Then chain rule times the derivative of the inside, which here is just 2. Which we could at least reduce a little bit then. Yep. Questions on this page? All right, let's turn the page. Okay, so we are tasked with finding the point on the exponential graph where the tangent line is perpendicular to some other line. Okay, so if it's perpendicular to this line, what would our slope need to be? So if it's perpendicular to this given line. Yeah, opposite reciprocal. So the slope of this line is -5. The opposite reciprocal will be 1/5. Okay, so this is asking us, this question is asking us, at what xy point is the derivative of this graph 1/5? So we should probably derive it, huh? Okay, so let's see, it's an exponential, but its base is not e. So, what was the rule?
A to the u times ln a times the derivative of the inside.
Times derivative of the exponent, the inside, the u, whatever, the chain rule, which here, since it was just x, that'd be 1, so we wouldn't need to write it. And then plus 1, well, the derivative of a constant is 0. So here's our derivative. And we want to know, where is this equal to 1/5? So we'd have to solve it for x. mean, we could do that by hand, be pretty messy, right? We'd have to divide off the natural log 3. Then we'd have to do another logarithm. And we'd have it. This would probably be something where, this might be the case where we'd graph it and find that intersection point instead. So let's pull up your favorite grapher. Desmos, okay. I like Desmos too. Y equals 3 to the x times natural log of 3. And then our other one was y equals 1/5. Mission accomplished. Wait. That's not what I had in my notebook. Is this right? Huh. Either I made a mistake here or I made a mistake in my notebook. I wonder which it was. I got, where's my Desmos? There's it is. Negative 1.5506. Okay. Oh, I know, because we got to find the point on the original graph. This is the derivative. Okay, that's why I have something here for my notebook. We hadn't finished the problem yet. So, Atif, what was it again? X equals. Okay. So then our original task was find the xy point. So we've just got to take this x value, plug it back into the original equation. That'll give us the full coordinate point. And since we only need to be accurate to 3 decimal places, we'll call that 1. And then we'll punch that into the y equation to get a y value, which, bippity boppity, okay, 1.18, 196, so 2. Cool. We did it. Save that for the next page.
Oh no. Hang on.
Alright, up next, we got x to the negative root 3 power. Now that's a weird exponent. How do we do this? Luke's got it. Is this an exponential function? So are we going to use the exponential rules? No. Nope. We're going to use the power rule. So let's bring down that weird exponent. Same base. And then subtract 1 from the exponent. Maybe I use a set of parentheses to show this is all in the exponent. Maybe I move it down. That wasn't bad. You gotta be careful. If you're used to thinking about exponential problems, it's easy to try and treat everything like it's exponential when it's not. So far we've encountered a couple cases, and I'll kind of debrief this on the side. We've had cases where we have We've had cases where we have a variable to a number. That's where we use the power rule. We've had cases where it's a number to a variable, and that would be where we use the exponential derivative rules. What if we had a number to a number? What do you think the derivative of that would be? 0, because the derivative of a constant is 0. Number to a number, that's still a number. 3 squared is 9. Whatever. Derivative of a constant is 0. The last case is when you have a variable to a variable. Turn the page.
Oh no!
What? What? It runs your calculator out of power, doesn't it? Okay. So, yeah, hey, he chose to take the quiz. I said I'll put the video up, but I suggested him staying for this. Okay. So, our last method, now the good news is this is our last method. This is called logarithmic differentiation. It is pretty much unrelated to the logarithmic rules from 2 pages ago. Sort of. It uses them, but it's not called logarithmic differentiation for that reason. So maybe you highlight this or write that at the top of your page. This here is where we're doing logarithmic differentiation. So we have a variable with a variable exponent. Variable base, variable exponent. What are we going to do? None of our rules help us with this. So that's it. We're done, right? None of our rules help. Hey, this is hard. Listen up.
Wait, what? That was so... You need to pay attention.
I actually... Sorry, I did not mean to come that close to you. This is the hardest thing. Please listen. Okay. So, none of our rules work on this. None of our rules work on this. We're going to adjust it to make our rules work. You know how you can multiply both sides of an equation by 5. You can subtract 10 from both sides of an equation. You can take the derivative of both sides of an equation. You can also take the logarithm of both sides of an equation. So, starting with this relationship is also true. Now, why would this help? It's one of, it's what?
I mean, isn't that one of our...
Well, right now we still have variable base, variable exponent.
Because it puts the 2x to the front. E to the power.
Not quite, not quite. Luke, you have an idea?
It becomes 2x times ln x.
Let's use one of those log properties.
Oh.
Now we don't have
I need to go wherever you came from.
base and variable, or sorry, variable in both the base and the exponent. Now our rules work. Bad news is it's not isolated for y, so you're going to have to implicitly derive it.
Why don't we just
Oh, because that's not how math works. That is what we like to call illegal. Illegal math. I'm going to send the math police on you. So now at this point, we're going to derive both sides of the equation. So we're going to derive both sides of this equation. On the left side, it's implicit. Hey, there's one of those rules we just learned with the logs. So it's 1 over inside times derivative of the inside, which dy dx, since our variables don't match, leave something behind. And then on the right side, we have a product rule, but at least it's kind of a basic product rule, right? So derivative, let's call this f, let's call this g. So df would be 2, g would be ln x, plus f dg. Derivative of natural log is 1 over the inside times derivative of the inside, but it's just x. Derivative of x is 1. So this actually nicely reduces. So really it's 2 natural log x plus 2. Oh, but we need to isolate the slope, right? Because that's the whole point. So let's just multiply everything by y. Or if you insist, divide everything by 1 over y, but that sounds terrible. Well, we started with a function. we started with a function. We should probably end with a function, right? No? Just done. That's it. No. This last thing is easy. It's easy. To get back to something as a function of x, you just need to get rid of the extra variable. Oh, hey, we have something for that. So let's resub that out real quick. Because if you have an original function, this would be y as a function of x. We should probably be able to write our derivative as y prime as a function of x. So that's what we're trying to do here. So all we have to do is get rid of this y. We had a definition for it, so it's not so bad. X to the 2x times this stuff. Whoops, 2 natural log x. Good, I'm glad.
I understand that.
That's what I love to hear. All right, you want to try the next one?
Yes, please.
Let's do it. Let's have you try the next one. What's up?
We're doing your code?
Yes,
Okay.
do try. Please try. Okay. All right. So let's see. First off, I'll just run you through what the solution looks like, or what the answer looks like, and then I'll walk through the solution if you'd like to see it. There we go. So there's the solution, or there's the answer. And as long as you have something that's equivalent to that, that's fine. So obviously you could have the x sine x at the end, or I guess you could distribute it if you really wanted to. If you got there, good job. You could start working on your work quietly, but let me talk to the people who maybe didn't get there so I can step through this problem as well. So just like with the last one, you have a variable in the base and in the exponent, so we're going to use the trick of taking the natural logarithm of both sides of the equation. And then we're going to use the exponent in the logarithm rule to bring the sine x out front. At this point, then I'm going to take the derivative of both sides with respect to x. The left side, y is no longer isolated, so not only are you going to have to use the logarithm rule, but you're also going to have to use the chain rule, multiply by the derivative of y with respect to x. On the right side, we have a product rule. So let's call the first one f, let's call the second one g. So df would be cosine x, and then leave g the same, plus f times derivative of g, which would be 1 over x. There's nothing else inside the logarithm, so we don't need to worry about chain ruling it. And then finally, let's multiply both sides by y, and then resubstitute what it actually is. And again, I would substitute this out to finish with the original thing. Cool. Anyone still stuck? I'll come back.